Something is slowing down beneath the Atlantic Ocean, a current system the size of 30 Amazon rivers, moving heat from the tropics all the way to the Arctic. It has kept Europe livable for thousands of years. It controls where rain falls in Africa. It shapes hurricane seasons along the American coast. And scientists now say it may be the weakest it has been in over 1,000 years. New studies from 2024 and 2026 are no longer debating whether it is slowing. They are debating how close it is to a point where slowing becomes something else entirely, something the planet has not seen since the last ice age ended. If you enjoy this journey, hit like and subscribe. It really helps us keep going. Prepare yourself. We begin. Right now, something invisible is running beneath the Atlantic Ocean, and your life depends on it. Most people think of the ocean as just water, a big flat surface you fly over on the way to Europe. But underneath that surface, the Atlantic is doing something extraordinary. It is moving heat, constantly, without stopping, like a planetary heating system that has been running for thousands of years. Here is the basic picture. The sun heats the tropics more than anywhere else on Earth. That heat has to go somewhere. If it just stayed near the equator, the tropics would burn and the poles would freeze solid. But the ocean absorbs that heat and carries it north. The Atlantic is one of the main highways for that job. Warm water flows up along the surface from the Gulf of Mexico and the Caribbean all the way toward Europe and the Arctic. As it travels, it releases heat into the air above it. That is why London, which sits at roughly the same latitude as parts of Canada, stays warm enough to have parks in winter instead of 3 feet of snow. Scientists call this system the Atlantic Meridional Overturning Circulation. Most researchers just call it the AMOC. Think of it as the Atlantic's engine. It does not just move water, it moves energy. The energy that keeps about 900 million people in Europe and the North Atlantic region living in conditions that are far milder than they should be at those latitudes. But that is only half of what the AMC does. When that warm surface water reaches the far north, something happens to it. It cools down. As it cools, it gets denser. Then it sinks. Deep into the ocean, it turns and flows back south along the seafloor, making room for the next wave of warm water coming up behind it. The whole loop keeps moving. Surface water goes north and releases heat. Deep cold water returns south, over and over. This loop carries the same amount of water as roughly 500 Mississippi rivers all moving at once. It is one of the largest systems of movement on the planet. And it does more than just warm Europe. The AMC helps decide where rain falls in the tropics. It influences how many hurricanes form in the Atlantic and how strong they get. It affects sea levels along the American East Coast. It connects to ocean systems as far away as the Southern Hemisphere. When it runs strong, billions of people benefit without ever knowing it exists. When it slows down, the effects ripple outward in every direction. Oceanographers have known about this system since the mid-20th century. For decades, it felt stable. Scientists knew greenhouse warming could eventually threaten it, but the model suggested the danger was far off. Something to worry about for future generations. That view has changed. Sharply. Multiple recent studies now point to signs of weakening that have been building for nearly 2 decades. Not a single bad year. A long, sustained trend across a system that most people have never heard of, controlling outcomes that most people experience every single day. The AMOC is not background scenery. It is active infrastructure. And scientists are increasingly watching it the way an engineer watches a bridge that has started showing cracks. The next question is why? What exactly makes this system run in the first place? And what could possibly bring something this massive to a halt? The answer starts with something you put on your food every day. Ask most people what keeps Europe warm, and they will say the Gulf Stream. They are not wrong, but they are describing a bicycle when the real machine is a skyscraper. The Gulf Stream is real. It is a powerful surface current that runs north along the American East Coast before swinging east toward Europe. You can see it on ocean maps. It has a colour, a temperature, a definite edge, where warm tropical water meets cooler Atlantic water. Ships have used it for centuries to make faster crossings, but the Gulf Stream is only the surface layer of something much bigger. The AMOC reaches from the surface all the way to the seafloor, more than 2 miles down in some places. It spans the entire Atlantic from the tropics to the Arctic. It includes not just the northward flow of warm surface water, but the return flow of cold, dense water creeping back south along the ocean bottom. The Gulf Stream is roughly the part of this system you can see from above. The AMOC is the whole building. This matters because when scientists talk about the system weakening, they're not just talking about the Gulf Stream's surface flow slowing down a little. They're talking about the entire overturning loop losing strength, the sinking, the return, the exchange of heat between the surface and the deep ocean. Here is a comparison that makes the scale clearer. The Gulf Stream carries about 30 million cubic yards of water per second near Florida. The full AMOC, at its peak overturning strength, moves water on a scale that dwarfs that. Think of the Gulf Stream as the visible river, and the AMOC as the entire underground water table beneath a continent. Another important detail: the Gulf Stream near Florida is partly driven by wind. That wind-driven portion is actually quite stable, and is expected to keep flowing, even if the AMOC weakens significantly. So surface measurements of the Gulf Stream can look normal, while the deeper overturning loop below quietly loses power. This is one reason early reassurances about the Gulf Stream being fine were misleading. Scientists measuring the wrong part of the system could find stable readings, while the more important deeper circulation was already in trouble. The confusion between the Gulf Stream and the AMOC is not just a public misunderstanding. It genuinely slowed down awareness of the problem. If the headline is Gulf Stream slowing, people picture a mild inconvenience. If the reality is the entire Atlantic heat engine weakening, the picture changes completely. There is also a popular culture problem. Movies and television have shown dramatic Gulf Stream shutdowns where Europe instantly freezes over in a matter of days. That version of events is not accurate. The real concern is slower, and in some ways more dangerous. A gradual weakening that shifts climate patterns over decades, less dramatic on screen, far harder to adapt to in real life. Understanding the difference between the Gulf Stream and the AMOC is the first step to understanding why scientists are worried now in a way they were not 20 years ago. Because what they are tracking runs far deeper than any surface current, and what they have found goes back to a single ingredient that holds the whole system together. Picture a conveyor belt at an airport. Bags go on at one end, travel along the belt and come off at the other. Now make that conveyor belt the size of the entire Atlantic Ocean. Make it run in 3 dimensions, from surface to sea floor. Make it carry heat instead of bags. That is the rough shape of the AMOC. It starts in the tropics, where the sun pours enormous energy into the ocean. The surface water warms up. It is also salty from all the evaporation in those warm regions. Warm and salty, this water flows north along the surface, pushed by winds and pulled by the density differences in the ocean ahead of it. As it travels north toward Greenland and the Arctic, 2 things happen. First, it releases its heat into the atmosphere. This is the part that warms Europe and moderates North Atlantic weather. Second, it cools down as it moves into colder latitudes. Cold water is denser than warm water. Salty water is denser than fresh water. So this water, having released its heat, becomes very dense enough to sink. When it reaches the deep waters near Greenland and Iceland, it drops. Not slowly. These are areas of active, powerful downwelling where surface water plunges to depths of 1 mile or more. This sinking is the engine of the whole system. It is what creates the pull that draws new warm water north from the tropics. Remove the sinking, and the conveyor slows down or stops. Once it has sunk, the water travels south along the ocean floor. Cold, dense, and oxygen-rich from its time at the surface, it flows as a deep bottom current back toward the equator and eventually into the South Atlantic and beyond. This deep return flow takes centuries to complete its full journey. Then, far to the south, that cold, deep water eventually rises back toward the surface, warms again, and the loop continues. The whole cycle is called thermohaline circulation. Thermo means heat, haline means salt. The system runs on the combined effects of temperature and salt content changing the density of seawater. Think of it like a lava lamp. Hot fluid rises, cools at the top, becomes denser, sinks, warms at the bottom and rises again. The amok works on the same basic principle, just scaled to an entire ocean and running on timescales of decades to centuries. There is one fragile point in this whole system, the sinking step. Everything depends on that surface water becoming dense enough to sink when it reaches the North Atlantic. If something interferes with that sinking, the conveyor loses its engine. And there is one thing that can block the sinking more effectively than almost anything else. Something that has been pouring into the North Atlantic in growing quantities for decades. Take a glass of water and add a handful of salt. Stir it. Now take another glass with plain fresh water. Drop a grape into each one. In the salty glass, the grape floats. In the plain water, it sinks. The ocean works the same way. Salt makes water denser. Denser water sinks. And in the amok, sinking is everything. When warm, salty water from the tropics travels north toward Greenland, it is doing so partly because of its density. As it cools, it becomes even denser. By the time it reaches the deep North Atlantic, it is cold enough and salty enough to sink rapidly. That sinking pulls more warm water in behind it, keeping the entire conveyor in motion. Remove the salt, or dilute it, and the water cannot sink. The engine stalls. This is the exact vulnerability that makes the amok so sensitive to what is happening in the Arctic right now. Greenland holds enough ice to raise global sea levels by about 20 feet if it all melted. Every year, that ice sheet sheds billions of tons of fresh water into the North Atlantic. Freshwater is the opposite of saltwater. It is less dense. When it pours into the ocean near the sinking zones, it dilutes the salty surface water, making it lighter, making it resist sinking. Think of it like someone pouring plain water into the top of your lava lamp. The hot fluid can no longer rise to the top properly. The circulation slows. Scientists have known about this mechanism for decades. It was always part of the long-range concern about climate change and the amok. But two things have changed recently. First, Greenland is losing ice much faster than older models predicted. Second, increased rainfall and runoff in the Arctic are adding even more fresh water on top of the meltwater. Both of those freshwater sources are growing together year after year. There is also a feedback loop buried here. A warmer planet melts more ice. More ice melt sends more freshwater south. More freshwater weakens the amok. A weaker amok allows the Arctic to get even warmer because less heat is being pulled away from the tropics to cool the high latitudes, and warmer Arctic means more melting. Each step feeds the next. The salt content of the North Atlantic surface is measurable. Scientists watch it carefully. The data has been showing the surface growing fresher for years in the areas where sinking is supposed to happen. The amok has been dealing with freshwater inputs for thousands of years. Ice ages and warm periods have always brought changes. But the rate of change today is faster than anything in the modern record, and the system is being pushed from multiple directions at the same time. What was once a distant theoretical risk is now a measurable process, and scientists have spent years building the tools to actually watch it happen in real time. The worry about the amok goes back further than most people realise. This was not a discovery made last year. The warning signs started piling up long before the public started paying attention. In the second half of the 20th century, climate scientists were already running computer models that included the amok as a critical piece of Earth's climate machinery. Even in early models, the same result kept appearing. Push enough greenhouse gases into the atmosphere, warm the planet enough, melt enough ice and increase enough rainfall, and the North Atlantic overturning circulation would weaken. The models varied on how much and how fast, but the direction was consistent. By the 1990s, enough evidence had accumulated that several serious climate research groups flagged the amok as one of the most important potential tipping elements in the entire climate system. A tipping element is a part of the Earth's systems that can switch states. Stable for a long time, then push past a threshold, it moves to a new stable state that looks nothing like the old one. The amok had all the features of a classic tipping element. It had been observed doing exactly this in the deep past, during ice ages and during rapid climate transitions. Scientists knew it was capable of switching. They just did not know how close to that switch the modern world was operating. Then, in 2004, something changed. A network of scientific moorings anchored at roughly the same latitude across the Atlantic began sending back real data about the AMOC's actual strength. For the first time, humanity had direct, continuous measurements of the most important current system on Earth. What the data showed over the following years was not reassuring. There were fluctuations as expected. The AMOC varies from year to year and even from decade to decade. But underneath the noise, some researchers saw something that looked like a longer downward trend. Others were cautious. The record was still young. A decade of data is a blink for a system that operates on century timescales. Still, by the early 2010s, a wave of scientific papers started pulling together different lines of evidence. Sediment cores from the ocean floor, temperature patterns in the North Atlantic, salinity measurements, sea surface temperatures in a region south of Greenland that had been cooling strangely even as the rest of the planet warmed. Each piece of evidence on its own had room for doubt. Together they were pointing in the same direction. Then came a study in 2021 that caught worldwide attention. Researchers looked at a kind of indirect fingerprint in ocean temperatures stretching back over 1,000 years and concluded that the AMOC was now weaker than at any point in that entire period. For a system that had been called stable, that was a startling claim. The scientific debate that followed was intense. Some researchers questioned the methods, others supported the findings, but the overall trend in the research was unmistakable. The alarm bells were ringing louder, and the system the scientists were watching was about to give them something even harder to dismiss. In 2004, scientists did something that sounds simple, but was actually a major engineering achievement. They anchored a series of instruments across the Atlantic Ocean at about 26 degrees north, roughly in a line between the Canary Islands and the Bahamas. These instruments measured temperature, salinity, and ocean current speeds. They transmitted data in real time, and they never stopped running. This network is called the Rapid Observing Array. It is the world's first and longest continuous direct measurement of the AMOC. Before Rapid, scientists had to rely on occasional ship-based measurements taken years apart. Trying to understand a planetary circulation system with those snapshots was like trying to understand a river by dropping a bucket in it once every 5 years. Rapid changed that. It gave scientists a real-time window into the strength of the Atlantic's engine. What Rapid measures at that single latitude is roughly how much water is overturning at that point, how much warm water is moving north near the surface, how much cold water is returning south in the deep. The difference between those two flows gives an estimate of the overturning strength. The numbers that came back were immediately interesting and troubling in equal measure. The record showed significant variation. Some years the AMOC was stronger than average, some years weaker. In 2009 and 2010, there was a dramatic dip, the weakest values the array had recorded up to that point. Then it partially recovered. But here is the part that started to worry researchers more than the dips themselves. Across the full record from 2004 to the present, the AMOC has not recovered to the level seen at the start of monitoring. The trend line, despite year-to-year swings, bends downward. There is an obvious limitation here. One measuring line across one latitude does not capture the full AMOC. The circulation has components and flows across the entire Atlantic basin, from the tropics to Greenland, from the surface to the seafloor. Rapid sees one slice. Scientists have been working to fix that limitation. More moorings have been added at other latitudes. In 2026, a study using 4 western boundary mooring sites spanning from roughly 16 degrees north to 42 degrees north detected weakening signals at every single location across nearly 2 decades of observation. That is not one spot. That is a spread covering more than 1,600 miles of ocean. And still, the full record is only about 20 years long. For a system that can shift on timescales of centuries, that is a very short window. Scientists are well aware of this. It is one reason the debate about timing remains so intense. But a short record showing consistent weakening is still a warning, especially when other types of evidence from sediment cores, temperature patterns, and model simulations are all pointing the same direction. The rapid array is the clearest instrument scientists have, and what it has measured over 20 years makes it very hard to claim everything is fine. What comes next reveals something even more unsettling, hiding in plain sight in the ocean's temperature patterns. There is a patch of ocean south of Greenland and Iceland that has been doing something strange. While the rest of the world's oceans have been warming steadily, this particular region has been cooling, or at best refusing to warm along with everything else. Scientists call it the cold blob, or sometimes the North Atlantic warming hole. It sits right in the area where AMOC's surface water normally releases its heat and sinks, and its behaviour has become one of the most closely watched indicators of what the Atlantic's overturning system is doing. Here is why it matters. When the AMOC is running strong, it delivers large amounts of warm, salty water to that region. The water releases heat, the area stays relatively warm, and the system keeps cycling. But when the AMOC weakens, less warm water arrives. The surface cools, the cold blob grows. So a cooling patch in a warming ocean is, paradoxically, a sign that something is wrong with the system that used to keep it warm. Think of it like a broken radiator in a room. If the radiator stops working, that corner of the room gets cold even while the rest of the building heats up from external sources. The cold spot is not a mystery, it is a symptom. Researchers looking at the cold blob have used it as an indirect measurement of AMOC's strength stretching back much further than the rapid array's 2 decades. By combining temperature records from ships, buoys and satellites going back over a century, they can trace the blob's behaviour through time and estimate how the AMOC has varied during that period. The pattern that emerged was concerning. The blob has been growing. The cold anomaly in that region, compared to what temperatures should be given global warming, has become more pronounced over the past several decades. That is consistent with the long-term AMOC slowdown. The cold blob is also not just an ocean surface curiosity. It has real effects on weather. A large cold patch in the North Atlantic shifts the temperature gradient between the ocean and the continent nearby. That can alter storm tracks, affect precipitation patterns, and change wind behaviour across a significant stretch of the Northern Hemisphere. Some researchers have suggested that unusual weather patterns over Europe and the American East Coast in recent decades may partly reflect the cold blob's influence. The attribution is still debated, but the mechanisms are physically plausible. What is harder to debate is the blob's existence and its connection to the region where AMOC sinking is supposed to happen. The data is there, the satellite images are there, a persistent cold anomaly in a warming ocean, sitting exactly where you would expect to see one if the Atlantic's engine was losing power, and there is a reason to pay close attention, because the fresh water flooding into that same region from Greenland is not slowing down. Every summer, the Greenland ice sheet melts a little. This is normal, it has always happened. In winter, snow replenishes what the summer lost, and the ice sheet stays roughly balanced. That balance is broken now. Greenland has been losing ice at an accelerating rate. In recent decades, the ice sheet has been shedding hundreds of billions of tons of ice per year, beyond what snowfall can replace. That ice does not disappear into the air, it flows into the ocean as meltwater, pouring into the exact region where the AMOC depends on surface water being dense enough to sink. Fresh meltwater is lighter than the salty ocean water around it. It sits on top. It insulates the surface from the colder air above, slowing further cooling. And critically, it dilutes the salinity of the surface layer, making that water less able to become dense enough to sink into the deep ocean. Picture a kitchen drain with a thin film of oil sitting on top of the water. The oil floats. The water below cannot escape easily. The drain slows. That is roughly what fresh water does to the AMOC's sinking mechanism. It forms a lid that the dense, salty deep water cannot get through. Greenland meltwater is only one source. Arctic sea ice, which has been declining dramatically, also releases fresh water as it melts. Increased rainfall in the Arctic, driven by a warmer atmosphere, adds more. Rivers draining from Siberia and northern Canada contribute fresh water into the Arctic Ocean, which connects to the North Atlantic. Each source is manageable in isolation. Together, over decades, they add up to a sustained freshwater injection into the most sensitive part of the Atlantic circulation system. Scientists have been measuring the salinity of the North Atlantic surface water at the key sinking regions for years. The data shows a freshening trend. The surface water in those areas is becoming measurably less salty over time. That freshening is exactly the fingerprint you would expect to see if freshwater inputs were accumulating faster than the ocean's natural mixing could handle them. What makes this particularly dangerous is the feedback element described earlier. A fresher surface means weaker sinking. Weaker sinking means less warm water pulled north. Less warm water pulled north means the Arctic gets warmer. A warmer Arctic melts more ice. More ice melts sends more fresh water south. The cycle tightens, and here is the detail that makes scientists most uncomfortable. The freshwater inputs are not coming from a single source that could be switched off. They are coming from the general warming of the entire Arctic system. As long as the planet keeps warming, the freshwater pressure on the AMOC keeps growing. The system is not being poked, it is being pushed. And recent measurements have found the pushing is already visible across a far wider stretch of the Atlantic than anyone expected. Imagine you are monitoring a power grid for a city. You have sensors at 4 different substations spread across hundreds of miles. One sensor showing a drop might be a local issue. 2 sensors showing drops might be a coincidence. All 4 showing drops at the same time over the same long period is a systemic problem. That is where AMOC scientists now stand. For years, the main direct measurements came from the Rapid Array, that single east-west line of instruments at 26 degrees north. It showed weakening trends, but critics could fairly point out that one latitude slice is not the whole ocean. Maybe the changes at that location reflected local conditions rather than a broad system-wide shift. Then in 2026, a team from the University of Miami published results from 4 western boundary mooring sites. These were not all clustered together. They spanned from about 16 degrees north all the way to 42 degrees north, covering a stretch of the western Atlantic roughly as long as the distance from Miami to Boston and beyond. At every single site across nearly 2 decades of data, the researchers found weakening signals. That span is critical. The western boundary of the Atlantic is where the return flow of warm surface water runs northward most strongly. It is where the fingerprint of AMOC strength is clearest. Finding consistent weakening across 1,600 miles of ocean at 4 independent locations rules out the local anomaly explanation. The researchers describe this as strong observational evidence for a broad-scale slowdown of the Atlantic circulation, not a localized quirk. To make the picture even clearer, these western boundary changes connect to what the Rapid Array has been recording at its own latitude. The signals are consistent. They are not contradicting each other. They are building a case, and the case now reads like this. Over roughly the past 2 decades, the AMOC has been losing strength across a wide swathe of the North Atlantic. The weakening is showing up in multiple independent data sets. The surface water in the sinking regions is getting fresher and lighter. The cold blob south of Greenland is expanding. The Rapid Array trend line bends downward. None of these alone would be a final answer. Together they are harder to wave away. Scientists are careful about language here. A weakening trend is confirmed by observations. Whether that weakening is already irreversible or how close it sits to a tipping threshold is still actively debated. But the gap between those 2 questions matters more than most people realize, because the models that are now matching the real-world observations best are also the ones that were once considered the extreme outliers. 20 years is a long time in a human life. You can go from being a newborn to graduating high school in 20 years. But for an ocean circulation system that has been running continuously for thousands of years, 20 years barely registers, except when those 20 years show a consistent trend in the same direction. The Rapid Array started collecting continuous AMOC data in 2004. By 2026, it had produced the longest uninterrupted direct record of Atlantic overturning strength ever assembled. When scientists look across that full span of data, they see something that looks like a declining system. The raw data is noisy. The AMOC varies seasonally, it varies year to year. Some years it is stronger than average and some years much weaker. The dramatic low point in 2009 and 2010 was followed by partial recovery. That kind of natural variation makes it easy to argue that nothing systematic is happening. But statistical analysis of the full record tells a different story. Strip out the short-term noise, average over longer periods, and the trend bends downward. The AMOC measured at that latitude has not returned to the strength levels seen at the start of the record, even during its stronger years in the later part of the dataset. That type of declining trend is exactly what you would expect to see if the underlying system was losing energy over time, rather than just bouncing around a stable average. The University of Miami study from 2026 added an important piece on top of this. By extending measurements across 4 sites from the subtropics into the mid-latitudes, researchers showed the trend is consistent with what the rapid array found. The system is not just weakening at one latitude, it is showing the same pattern across the entire reach of the Western Atlantic boundary current. 2 decades of observation is still short for a system this old. Scientists are honest about that limitation. They cannot yet rule out the possibility that some future natural uptick in circulation strength will reverse the trend. But 2 decades of consistent weakening, confirmed across multiple independent observation systems, combined with physically understood mechanisms involving freshwater inputs and warming temperatures, builds a compelling case. Scientists who study natural variability are finding it increasingly difficult to explain the full pattern as random noise. The physical explanation, freshwater from Greenland and the Arctic diluting the sinking zones, fits the data too well. And 2026 brought a new study that made the numbers even harder to ignore. One that directly challenged the moderate forecasts many governments and media reports had been relying on for years. Climate models are some of the most sophisticated tools humans have ever built. They simulate the atmosphere, oceans, ice sheets, land surfaces, and their interactions using equations that fill entire server farms. They have improved enormously over the past few decades, but they are not all equal. And when it comes to the AMOC, some models have been consistently too optimistic. Here is how this works. Scientists run many different climate models from many different research groups around the world. Each model makes slightly different assumptions about ocean mixing, freshwater inputs, ice sheet behavior, and dozens of other factors. The usual approach in summary reports is to average across all the models to get a central estimate and show the range as uncertainty. For the AMOC, that averaging approach has created a problem. Some of the models in the ensemble are much better than others at simulating observed AMOC behavior. They reproduce the cold blob, they match the salinity patterns in the North Atlantic. They capture the weakening trends seen in the rapid data. These models tend to project stronger future AMOC weakening. They were often treated as outliers, extreme cases sitting at the pessimistic end of the range. Other models reproduce the AMOC less accurately, but pull the average toward a more moderate outcome. In 2026, a research team approached this problem differently. Instead of treating all models equally, they compared each model's historical performance against actual AMOC observations, and weighted the results accordingly. Models that matched reality better got more influence over the projections. Models that failed to reproduce observed behavior got less. The result was striking. The models that best match real-world AMOC behavior also projected the most significant future weakening. When the analysis was constrained to those better-performing models, the projected slowdown by the year 2100 landed in a range of 43 to 59% weaker than the mid-20th century baseline. That is not at the edge of a range anymore. That becomes the likely outcome according to the models that actually work. CNN reported this was roughly 60% more severe than the multi-model average that older summaries had used. 60% is not a minor revision. It means the projections that governments and planning agencies had been treating as worst-case scenarios may actually be closer to central estimates. The scariest models were not outliers, they were the accurate ones. This is the part of the AMOC story that has most changed the tone among scientists. The question is no longer whether old forecasts were too optimistic. The question is how much too optimistic they were. And underneath all of these projections sits a deeper concern. The models are forecasting gradual weakening. But the AMOC may not weaken gradually forever. Numbers only mean something when you can picture what they represent. So before moving forward, it is worth stopping to understand what a 43 to 59% weakening of the AMOC actually looks like in the real world. The AMOC in its current state, already weakened from what it was in the mid-20th century, still moves an enormous amount of heat. It transports roughly 1.25 billion watts of energy northward in the Atlantic. That number is almost impossible to picture directly, so try this instead. The total electrical generating capacity of every power plant in the United States, all of them running at full capacity at the same time, is somewhere around 1 trillion watts. The AMOC moves heat equivalent to more than 1,000 times that, every second, continuously. Cut that by half, and the effects are not subtle. The 2026 study, which matched AMOC projections to the models that best represent observed reality, concluded that a roughly 50% weakening by 2100 is a realistic central estimate, not a fringe scenario. That conclusion came from filtering out models that failed to reproduce real North Atlantic behaviour and letting the better performing models carry the weight of the projection. What researchers found was that the models most consistent with observed salinity patterns, the cold blob behaviour, the rapid array measurements, and the multi-site western boundary slowdowns all clustered toward the more severe end of the old range. Put another way, the IPCC and many government assessments had been presenting a moderate scenario as the average expectation. The 2026 analysis suggests the moderate scenario was inflated by poorly performing models. The implications stretch beyond just the number itself. A 50% weaker AMOC changes the heat distribution across the North Atlantic. It shifts how much warmth reaches Europe. It affects the temperature gradient that drives weather systems across the entire basin. It changes where tropical rainfall falls. It alters hurricane development conditions. It drives additional sea level rise along Atlantic coastlines. Each of those consequences scales with how much the AMOC weakens. A 10% weakening produces modest effects. A 50% weakening produces major ones. The gap between those two outcomes represents the gap between manageable disruption and significant reorganization. And this is still the gradual weakening scenario. The models project a trend. They do not automatically include what happens if the system reaches a tipping threshold and shifts abruptly. That possibility is what the next layer of research has been focused on almost exclusively. Because some scientists are no longer asking how much the AMOC will weaken. They're asking whether it will stop. The word tipping point gets used a lot. It shows up in politics, in business, in everyday conversation. But in climate science, it means something specific, and understanding what it actually means is essential to understanding why the AMOC story is so disturbing. A tipping point is a threshold. Below that threshold, a system responds proportionally to pressure. Push it a little, it changes a little. Push it harder, it changes more. But the system stays in the same basic state. Remove the pressure, and it tends to recover. Past the threshold, the system enters a different regime. The change becomes self-sustaining. It no longer needs the original push to keep going. And crucially, removing the pressure does not automatically reverse what happened. The system has moved to a new stable state. A classic simple example is a pot of water on a stove. You can heat it gradually and it stays liquid. The temperature rises smoothly. But there is a specific temperature at which the water transitions to steam and the behavior changes completely. That transition is not just more of the same, it is a state change. The AMOC has a built-in structure that makes it a candidate for this type of behavior. The overturning loop depends on water being dense enough to sink in the North Atlantic. Sinking drives the whole system. But here is the trick. A weaker overturning means less salty water is pulled north from the tropics. Less salty water arriving at the sinking zones means the surface there becomes fresher. Fresher water is less dense and sinks less effectively, which weakens the overturning further, which brings less salty water north, and so on. This is a self-reinforcing feedback loop. Once it gets going past a certain point, it drives itself. No additional external pressure needed. Scientists call this a salt advection feedback, or the Stommel bifurcation after the oceanographer who first described it mathematically in 1961. The idea that the Atlantic could have two distinct stable states, one with strong overturning and one with weak or collapsed overturning, has been in the scientific literature for over 60 years. What has changed recently is the assessment of how close the modern AMOC is operating to that bifurcation point. Older estimates placed it comfortably far away. Newer estimates, based on better observations and improved analysis, suggest the margin may be much smaller. Small margins in a self-reinforcing system are not reassuring. The moment the AMOC crosses its tipping threshold, the behaviour changes from gradually weakening to something moving toward a new stable state. And that transition, according to one major recent study, can unfold on human timescales. That study came from a university in the Netherlands, and what it described made some of the most experienced climate scientists in the world genuinely uncomfortable. In 2024, researchers at Utrecht University in the Netherlands published a study in the journal Science Advances that put the tipping point question in sharper focus than almost any previous work. Their central finding was this: the AMOC is moving toward a tipping point, and once it crosses that threshold, the transition to a weak or collapsed state could happen surprisingly fast by human standards. The word fast here is doing a lot of work, so it needs to be unpacked carefully. In geological terms, fast can mean thousands of years. In ocean science, fast sometimes means centuries. What the Utrecht team found was something more alarming. Their analysis suggested the actual reorganisation of the overturning system, once the tipping threshold is crossed, could unfold over decades, perhaps within a human lifetime. That is the detail that shifted the conversation. Most climate risks operate on scales that allow for gradual adaptation. Sea levels rising a few inches per decade, average temperatures creeping up over generations. Those timescales are already challenging. But they give societies some time to respond, to build seawalls, to move crops, to change infrastructure. A system that crosses a threshold and then reorganises within decades does not offer that window. It crosses a line that looks like just another bad year, and then it changes far faster than institutions can plan for. The Utrecht study used a specific type of mathematical analysis, focused on how systems behave near tipping points. They looked for what scientists call early warning signals, subtle changes in how the AMOC varies that suggest it is losing its ability to recover from perturbations. A system approaching its tipping point tends to show slower recovery from disturbances. It starts to wobble differently. Their analysis found those signals in the AMOC data. Importantly, the study did not claim the tipping point had already been crossed. It claimed the system was moving toward it, and that the direction of movement was concerning. The difference between approaching a tipping point and being past it is enormous. One is a warning, the other is an outcome already in motion. But a warning only helps if it is heard clearly. And for years, the loudest reassurances in public discussions of the AMOC came from summary documents that leaned on model averages now shown to be too moderate. The Utrecht findings added weight to a growing scientific discomfort. Several other research groups had been running similar early warning analyses with similar results. The AMOC was not just weakening. It was showing the specific kind of instability that physical theory predicts in a system approaching a state change. What nobody could yet say with certainty was when. And that question of timing became the most contested and most urgent piece of the entire AMOC puzzle. If scientists could agree on one thing about the AMOC's future, timing would be it. But timing is exactly where they disagree most sharply, and the range of estimates is wide enough to matter enormously. On one end, the IPCC 6th Assessment Report, published in 2021, said there was medium confidence that the AMOC would not collapse abruptly before 2100. That is a cautious statement from a document designed to represent consensus. It does not say collapse is impossible. It says abrupt collapse before 2100 is unlikely according to the weight of evidence available at the time of writing. On the other end, some researchers have pushed the danger much closer. A 2024 timing analysis that received wide press coverage, though it had not yet passed peer review at the time, estimated a possible window for significant AMOC disruption stretching from 2037 to 2064, with some calculations suggesting a greater than 50% chance of serious transition by 2050. Between those two positions sits the Utrecht study, and several other peer-reviewed analyses from 2024 that place serious tipping risk within this century without committing to a specific year. Why is the range so large? Several factors contribute. The observational record is short. Direct AMOC measurements only go back to 2004. Trying to project when a planetary system will cross a threshold based on 20 years of data is like trying to predict when a long novel ends after reading the first chapter. The freshwater input from Greenland is also deeply uncertain. How fast the ice sheet loses mass over the coming decades depends on how fast global warming proceeds, which depends on human emissions choices that have not yet been made. A high emissions future accelerates Greenland melt and pushes fresh water into the North Atlantic faster. A lower emissions future slows that process. Different models also handle the salt advection feedback differently. Some simulate it as a strong driver toward instability. Others treat it as weaker. Those differences compound over time and produce very different timing estimates by the end of the century. What the experts who remain skeptical of near-term collapse and those who see it as plausible by mid-century do agree on is this. The AMOC is weakening. The freshwater pressure is increasing. The system is not stable, and the consequences of being wrong in the optimistic direction are far larger than the consequences of being wrong in the pessimistic direction. That asymmetry is part of what makes the AMOC debate matter beyond academic journals, because unlike most scientific uncertainties, this one has a hard edge. Cross the threshold and some outcomes become locked in, regardless of what happens to emissions afterward. The IPCC, the Intergovernmental Panel on Climate Change, is the closest thing the scientific world has to an official summary of climate knowledge. Every several years, hundreds of scientists from around the world review thousands of studies and distill the findings into reports that governments use to make policy decisions. On the AMOC, the most recent full assessment said this: the overturning circulation is very likely to weaken over the 21st century. An abrupt collapse is unlikely before 2100. The overall tone was serious but not alarmist. That assessment reflected the best available evidence when it was written, but it was finalised using data and studies available up to a certain point in time. Science does not stop when a report is published. The 2024 and 2026 studies came after that cutoff, and several of them directly challenged the assumptions that led the IPCC to its more conservative conclusions. The model weighting study from 2026 is perhaps the clearest example. When researchers filtered out the poorly performing models and let the better performing ones drive the projections, the central estimate for AMOC weakening shot well past what the IPCC's multi-model average had suggested. The IPCC's range was not wrong to include the possibility. It was potentially wrong to treat moderate outcomes as the central expectation. The early warning signal studies also postdate the IPCC assessment. The mathematical analysis showing the AMOC exhibiting tipping point-like behaviour was published after the report's data cutoff. This does not mean the IPCC was wrong. It means scientific understanding has moved. The IPCC process is inherently conservative. It requires consensus across a large body of researchers and is designed to avoid overstating uncertainty or catastrophizing. Those are appropriate values for a document that drives global policy. But they also mean the official summaries can lag behind where the leading edge of research actually is. Several researchers who worked on or contributed to IPCC processes have said publicly that the evidence now points to higher risk than the last full assessment captured. That is not a criticism of the process. It is an acknowledgement that evidence keeps coming in. The gap between the IPCC's 2021 conservative position and the more alarming findings of 2024 and 2026 is not a contradiction. It is the normal operation of science. New data changes estimates. But when those estimates are being used to plan coastal infrastructure, agricultural systems and city layouts designed to last 50 years or more, the gap between the old middle estimate and the new middle estimate represents real decisions being made on outdated information, and governments are not the only ones who need to understand what updated projections mean, because what the latest research describes hitting the coasts, the farms and the cities of the North Atlantic is not just a percentage on a chart. Speed is the part of the AMOC story that turns a serious problem into a civilizational one. A slow, gradual weakening is bad. A 50% drop in circulation strength by 2100 means a century of adapting to new weather patterns, shifting rainfall, colder European winters, and rising seas along the American East Coast. That is an enormous challenge. But a century gives engineers, planners, farmers, and governments some time to respond. Buildings get upgraded, crops get shifted, coastal defences get built. A fast collapse is a different category of problem entirely. When scientists use the word abrupt in the context of the amok, they do not mean it collapses overnight. They mean it reorganises on a timescale that is fast relative to the planning cycles of human civilization. Years to decades rather than centuries. The Utrecht study's contribution to this question was specific. Their mathematical analysis suggested that once the amok crosses its tipping threshold, the actual transition to a new weakened or collapsed state could occur within decades, not at the end of a century, not in the slow background of geological time, decades, within the lifespans of people alive today. Now picture what a decade-scale reorganisation of Atlantic circulation actually means in practical terms. European agriculture is calibrated to current climate conditions. Farmers choose crops, planting schedules, and irrigation systems based on the climate their region has experienced for the past century. A rapid cooling of several degrees Celsius across Western Europe within a generation would render those choices wrong simultaneously for millions of farms, not gradually, not giving each generation time to adjust, all at once. Coastal cities on the American East Coast from Miami to Boston sit on infrastructure built to handle current sea levels, with some margin for gradual rise. A rapid AMOC shift adds regional sea level rise on top of global warming-driven rise in that same stretch of coast. The infrastructure was never designed for that combination arriving fast. Tropical rainfall belts, which feed agriculture across West Africa, the Sahel, and parts of South America, would shift within timescales that seed selection programs and irrigation networks cannot easily follow. The deeper problem is that modern civilization is built for gradual change. Legal systems, financial systems, infrastructure investment cycles, food supply chains. All of these function reasonably well when conditions shift slowly enough that institutions can adapt one step at a time. A decade-scale reorganization of one of Earth's primary heat distribution systems breaks that assumption. Scientists who study societal resilience call this kind of risk a fast-onset systemic shock. The same general category as a major pandemic or a large asteroid impact in terms of how quickly institutions need to respond. But unlike those events, an AMOC transition would not announce itself dramatically in a single moment. It would build, cross a line, and then accelerate, while the world was still debating whether the line had been crossed. That is why the timing debate is not academic, and the effects would not stop at Europe's coast. London sits at roughly the same latitude as Calgary, Canada. Stockholm is as far north as the southern tip of Alaska. Amsterdam lines up with parts of Labrador, one of the coldest and most remote coastlines in North America. None of those European cities feel anything like their Canadian or Alaskan counterparts. London has parks in January. Amsterdam gets rain, not permafrost. Stockholm is cold in winter, but livable in ways that similar latitudes in North America are not. The AMOC is a large part of why. By delivering warm Atlantic water northward and releasing heat into the atmosphere above the ocean, the AMOC effectively subsidizes the climate of Western and Northern Europe. It is not the only factor. Prevailing winds matter too. But remove the AMOC's heat contribution, and the difference is dramatic. Studies estimating the cooling effect of a major AMOC weakening on Europe generally land on figures between 3 and 8 degrees Celsius of average temperature drop across parts of northwestern Europe over several decades. 3 to 8 degrees Celsius does not sound extreme until you consider what it means at ground level. In terms of growing seasons, 3 degrees of cooling pushes the agricultural calendar back by weeks. Crops that currently thrive in England, France, or Germany either shift northward, require different varieties, or fail entirely in some regions. Wine regions would move, wheat yields would drop. Northern European countries that currently import relatively little food because of productive domestic agriculture would face a very different situation. In terms of energy, heating demand across Europe would rise sharply. Countries that have been building infrastructure around milder winters would face energy systems inadequately sized for much colder conditions. The transition would be expensive and take years to complete. In terms of winter severity, regions currently accustomed to occasional frost would face conditions more like the interior of Canada. Cities whose infrastructure, road designs, pipe insulation standards, and building codes were calibrated for a different climate would struggle with conditions they were never built to handle. And here is the detail that makes this even harder to process. This cooling would arrive while the rest of the planet continues to warm from greenhouse gases. Europe would be getting colder as global average temperatures rise. That paradox is physically real. It would be deeply disorienting for the public, for politicians, and for the media trying to explain why Europe is freezing while everywhere else heats up. Some models suggest the regional cooling in parts of Europe could partially or fully offset greenhouse warming in those areas for a period of decades, before greenhouse warming eventually dominates again. That does not make the amok-driven cooling harmless. It means two large and opposing forces acting on the same region at the same time, producing volatility rather than stability. European cooling is the headline, but it is the smallest part of what an amok shift would actually do. Because while Europe adjusts to colder winters, the American coast would be dealing with something the sea has been quietly building toward for years. Most people think sea levels rise evenly, like filling a bathtub. Add more water, and every shore gets a little higher tide simultaneously. The ocean does not work that way. Sea level rise is uneven. It is affected by gravitational pull from ice sheets, by changes in ocean currents, by how land rises or sinks in different regions, and by heat expansion. Different coastlines experience different amounts of rise even from the same global change. The amok creates a specific sea level effect along the American East Coast that most people have never heard of. When the amok is running strong, it pulls water away from the American coastline. The northward flow of warm surface water in the western Atlantic actually draws water eastward and northward, keeping sea levels along the east coast lower than they would otherwise be. It acts like a subtle drain pulling water away from shore. Weaken or stop the amok and that drain effect disappears. The water it was pulling away redistributes. Sea levels along the American East Coast rise above and beyond whatever global warming is already adding. Scientists have estimated that a major amok weakening could add between 1 and 3 additional feet of sea level rise along parts of the East Coast by the end of this century, on top of the global average rise from melting ice and thermal expansion of warming water. For cities like Miami, New York, Boston, and Charleston, that extra rise is not a rounding error. Those cities are already managing infrastructure, flood insurance systems, and coastal defences calibrated to current sea level projections. Add an additional foot or more and every calculation changes. Flood zones expand, tidal flooding frequency multiplies, storm surge from hurricanes reaches further inland. New York City and Miami are both at serious exposure. Large sections of lower Manhattan and virtually all of South Florida sit within feet of current sea level. Planners have been working on adaptation strategies for decades, but those strategies assume a certain rate and amount of rise. AMOC-driven additional rise compresses the available response time. The East Coast sea level effect is not future speculation. Researchers have already detected that sea levels along parts of the American Atlantic coast are rising faster than the global average, and some of that excess rate is consistent with a weakening amok. The connection is measurable now, at current amok weakening levels. As the system weakens further, the effect strengthens. The American coast would be feeling the amok's absence in the most literal physical way. At the same time, thousands of miles away, entire agricultural systems would be watching the sky. The amok does not just move heat in the North Atlantic, it moves heat between the entire northern and southern hemispheres. When it runs strong, more heat ends up in the northern hemisphere. When it weakens, that balance shifts. The southern hemisphere gets relatively more heat. The northern hemisphere gets less. That hemispheric balance directly controls where the tropical rain belt sits. The tropical rain belt, sometimes called the intertropical convergence zone, is a band of intense rainfall that circles the Earth near the equator. It migrates north in the northern hemisphere's summer and south in winter following the warmth. Entire agricultural systems, ecosystems, and human settlements are built around where this belt brings rain and when. When the northern hemisphere cools relative to the southern, the rain belt shifts south, stays south longer, brings less rain to regions that depend on it during certain months. The West African Sahel is one of the most exposed regions on Earth to this kind of shift. The Sahel is a broad band of semi-arid land stretching across Africa just south of the Sahara. It receives most of its rain during a narrow monsoon window. The timing and intensity of that monsoon is sensitive to the position of the tropical rain belt. During past AMOC slowdowns in Earth's history, including events recorded in cave deposits and ocean sediments, the Sahel experienced severe droughts. The monsoon shifted south. The rains failed. A similar shift in the future would affect hundreds of millions of people who depend on Sahel agriculture for food. The region is already prone to drought and food insecurity. A southward shift in the tropical rain belt driven by AMOC weakening would push it closer to the edge of what is survivable for farming communities there. South and Central America face related risks. Parts of the Amazon basin and the Brazilian interior receive rainfall from moisture circulation patterns tied to the tropical rain belt. A sustained southward shift of that belt could reduce rainfall in some Amazon regions while increasing it in others, altering the water balance of one of the most ecologically critical areas on Earth. South Asian monsoons also have some sensitivity to North Atlantic conditions. The connections are less direct, but models suggest a major AMOC disruption would send ripples through monsoon systems that billions of people across India, Southeast Asia and China depend on for agriculture. The rain belt shift is one of the AMOSI consequences hardest to visualize from a European or American perspective. But in terms of human suffering per degree of climate change, it may be the most severe consequence of all. Billions of people live in the places where the tropical rain belt brings the only rain they get each year. If the belt moves, the water moves with it. And while the rain shifts, the storms are changing too. Atlantic hurricanes form over warm water. The warmer the water, the more energy available to feed a storm. The AMOC plays a role in controlling sea surface temperatures across the Atlantic, and that relationship means AMOC changes ripple through hurricane behaviour. When the AMOC is strong, it pulls warm surface water northward and away from some regions while delivering warmth to others. It also influences the temperature gradient between the tropics and the higher latitudes, which shapes the atmospheric wind patterns that either support or shear apart developing storms. A weaker AMOC changes that setup in several ways. First, without the northward pull of warm surface water, more heat can accumulate in the tropical Atlantic where hurricanes form. Warmer tropical waters, combined with the global warming-driven ocean heat, increase already underway, could intensify hurricane activity. More powerful storms forming from water that has more energy to give them. Second, changes in the temperature gradient between the tropical and subtropical Atlantic affect the wind shear patterns that storms have to fly through. Wind shear, a rapid change in wind speed or direction with altitude, tends to tear hurricanes apart before they can develop fully. AMOC changes could alter the shear environment across the Atlantic, affecting which areas become favourable for storm development and which become hostile. Third, a cooler North Atlantic south of Greenland, the cold blob signature of AMOC weakening, shifts the temperature contrast across the ocean. That contrast drives the atmospheric circulation patterns over the entire basin. Different contrast, different storm steering currents, different track probabilities for storms heading toward the American coast or turning out to sea. The precise future of the hurricane activity under AMOC weakening is still actively researched. Some models suggest more intense storms. Others suggest different track distributions. The uncertainty is real. What is not uncertain is that the Atlantic hurricane threat is shaped by the same ocean conditions the AMOC maintains. Change the ocean temperature pattern significantly, and the hurricane environment changes with it. Which direction the change pushes in any specific location depends on details that scientists are still working to pin down. But millions of people from the Gulf Coast to the Carolinas to New England sit in the path of Atlantic storms. They already face a warming ocean trend that is feeding stronger hurricanes. Adding a major AMOC reorganization on top of that baseline shift does not make the forecast calmer. The storms that shape the American coastline are sensitive to the same Atlantic engine that is now visibly weakening, and the consequences keep going, past the Americas, past the tropics, all the way to the other side of the planet. The AMOC's influence does not stop at the equator, it does not stop at the North Atlantic. Through a chain of ocean and atmosphere connections, a major disruption in Atlantic overturning would send effects ricocheting to places that seem impossibly far removed from a current system running between Florida and Greenland. The core reason is hemispheric heat balance. Right now, the AMOC moves a large amount of heat from the southern hemisphere into the northern hemisphere. It carries warm tropical water northward and exports the density-driven deep water southward. This northward bias in heat transport is constant and substantial. It means the northern hemisphere retains more heat than it would otherwise, and the southern hemisphere gives some of its heat away. Shut down or significantly weaken that northward heat export and the southern hemisphere starts retaining more of its own heat. The balance tips. Scientists studying this effect have found that a major AMOC slowdown could warm parts of the Southern Ocean. The Southern Ocean surrounds Antarctica. It plays a critical role in Antarctic ice sheet stability. A warmer Southern Ocean would increase melting of Antarctic glaciers and ice shelves from below, accelerating sea level contributions from the southern pole, so the AMOC weakening in the North Atlantic would, through this chain, increase the rate of ice loss from Antarctica in the south. And that additional ice loss feeds back into global sea level rise, above and beyond what happens in the northern hemisphere from Greenland. One problem feeding another. Australia is also sensitive to this shift. Researchers studying what an AMEAS collapse would mean for Australian climate found that the redistribution of heat toward the southern hemisphere could make La Nina conditions, which bring heavy rainfall to eastern Australia and drought to other regions, more frequent and persistent. A climate pattern that Australian agriculture already struggles to manage could become the new normal, rather than an occasional disruption. The tropical South Atlantic would warm. The South American monsoon systems would shift. Ocean circulation patterns around the tip of South America and throughout the South Atlantic would reorganize. All of this from a circulation system that most people, if they have heard of it at all, associate with keeping London from feeling like Calgary. The interconnections are real, the physics is understood. What happens in the North Atlantic sinking zones does not stay in the North Atlantic. It travels through the ocean and the atmosphere in ways that make the AMOC one of the most globally significant systems on the planet. And the systems that the AMOC ultimately threatens are not just weather patterns or ocean temperatures. They are the fields that feed us. Every major agricultural region on Earth developed under a specific set of climate conditions. Soil types, average temperatures, rainfall patterns, frost timing, and seasonal rhythms shaped what could grow, when to plant, and how much to expect. Farmers, over centuries, selected crops and techniques matched to those conditions. The AMOC underpins the stability of conditions across a large portion of the planet's most productive agricultural zones. Northwestern Europe is one of the world's most reliable food-producing regions. The United Kingdom, France, Germany, the Netherlands, and neighbouring countries grow enormous quantities of wheat, barley, potatoes, vegetables, and dairy products. That productivity depends on mild temperatures, reliable growing seasons, and the absence of severe cold snaps that kill crops or shorten the window between last frost and first frost. A cooling of several degrees Celsius across northwestern Europe, delivered over decades by a weakening AMOC, would push all of those assumptions out of calibration. Growing seasons would shorten. Some current crop varieties would fail. Frost risk would increase at both ends of the agricultural calendar. The dairy regions of England and France would face harsher winters than their infrastructure and herds can easily absorb. The Sahel, discussed in the context of rainfall shifts, is again central here. This region feeds tens of millions of people through subsistence and small-scale agriculture, entirely dependent on the annual monsoon. If the monsoon timing or intensity shifts south, because the AMOC is weakening the Northern Hemisphere's heat advantage, harvests fail. Famine pressure in an already stressed region intensifies. The American Midwest, the grain belt that feeds a large fraction of the world, is less directly exposed to AMOC cooling than Europe, but changes in Atlantic storm tracks, moisture delivery patterns from the Gulf of Mexico, and general atmospheric reorganization driven by a cooler North Atlantic all introduce new variability into a region whose entire agricultural model is built on predictability. Global food systems are also deeply interconnected. A simultaneous hit to European grain production, Sahel subsistence farming, and increased weather volatility across the American Corn Belt does not stay contained within those regions. It propagates through commodity markets, trade flows, and food prices worldwide. Countries that currently import most of their food, particularly in the Middle East, North Africa, and parts of Asia, would face price shocks and supply disruptions that their domestic systems cannot absorb. The AMOC does not just threaten coastlines and weather patterns, it threatens the supply chains that 7 billion people depend on for daily survival. And the cities those people live in were not built for the world that an AMOC shift would deliver. The world's major cities are enormous investments. The infrastructure beneath a single large city, the pipes, tunnels, foundations, electrical grids, transportation networks, and flood systems, represents spending accumulated over generations. Once built, it is not easily replaced. A subway system built in the 1920s is still running in the 2020s. A drainage system designed in the 1950s is still handling rain in the 2020s. All of that infrastructure was designed for the climate that existed when it was built, with some margin for reasonable future change. The AMOC problem exposes a dangerous assumption embedded in that design logic. City planners, when they factor in climate projections at all, are using estimates based on the models that have now been shown to underperform on AMOC behaviour. The moderate scenarios, the ones that drove most official planning guidelines, may significantly understate the actual future. New York City offers a useful example. After Hurricane Sandy in 2012, the city undertook substantial investments in coastal flood protection. Barriers, elevation requirements, updated flood maps, infrastructure hardening. Those investments were sized for a specific range of future sea level rise based on then current projections. An AMOC-driven additional foot or more of sea level rise on the American East Coast, on top of global projections, would push New York's exposure well beyond the range those investments were designed to handle. Miami faces an even more acute version of this problem. The city sits on porous limestone that makes underground flood barriers largely ineffective. It deals with tidal flooding on sunny days already, a phenomenon locals call sunny day flooding. Its entire water management system was built for a different sea level than what is arriving. An AMOC shift that adds extra regional rise to South Florida's coast would accelerate a timeline that engineers are already struggling to manage. London, on the other side of the Atlantic, faces its own version. The Thames Barrier was designed to protect the city from storm surges. It was built in the 1980s and was expected to require closure only a few times per year. It is now being closed significantly more often. Factoring in AMOC-driven cooling, potential shifts in North Atlantic storm tracks, and sea level changes, the barrier's design life is under increasing scrutiny. Rotterdam, Hamburg, Copenhagen. Every major coastal city in northwestern Europe faces a similar recalculation. The investments being made today in coastal infrastructure, transit systems, water networks, and urban housing will need to function for 50 to 100 years. They will need to function in whatever Atlantic climate emerges over that period. Most of them are being designed for a future that the latest AMOC science suggests is too optimistic. And the deeper problem is not that engineers do not know this, some do. The problem is that the early warning signals scientists use to track the AMOC's health are still being argued about, and one of the most important debates in all of climate science is whether those signals are already visible in the data. Before a system tips, it often wobbles. The wobbling is detectable if you know what to look for. Scientists have developed a set of mathematical tools specifically designed to detect early warning signals in systems approaching tipping points. The core idea is simple. A stable system that is pushed slightly off balance recovers quickly. A system close to its tipping threshold recovers slowly from the same kind of push. It wobbles more. It takes longer to settle. That change in recovery speed, detectable in the variability of a time series of measurements, is called critical slowing down. It is a general feature of many systems near tipping points, from ecological populations to financial markets to climate circulation. Researchers have applied these methods to AMOC data, and the results have generated real scientific controversy. A prominent 2021 study found what appeared to be early warning signals in Atlantic Sea surface temperature records going back to the 1870s. The analysis suggested the AMOC had been showing increasing critical slowing down over the past century, consistent with the system moving toward a tipping point. The paper received enormous media attention. It also received significant scientific pushback. Critics argued that the sea surface temperature record used in the analysis was an imperfect proxy for omic strength, and that the statistical method could produce apparent signals even in data where no real tipping behaviour exists. Other researchers pointed out that similar methods had falsely flagged warning signals in other ocean systems that had not subsequently tipped. The original authors defended their approach. They acknowledged the limitations but argued the signal was robust enough to take seriously. This debate has continued through subsequent studies. Some have supported the finding using different data or different methods. Others have raised methodological concerns. The scientific community has not reached a clear consensus on whether the early warning signals detected in the historical record are reliable indicators or statistical artifacts. What makes this debate matter beyond academic papers is the implications for urgency. If the early warning signals are real, and the AMOC is already in a state of critical slowing down, it means the system is considerably closer to its tipping threshold than it would otherwise appear. The window for precautionary action would be shorter. If the signals are statistical noise, then the AMOC may still have more time before approaching the threshold. Not infinite time, given the clear weakening trend in direct observations, but more time. Scientists on both sides of this debate are serious researchers working carefully on a hard problem. The disagreement is honest. But the stakes of the disagreement are enormous, and meanwhile, the one physical driver of AMOC instability that everyone agrees is accelerating is sitting on top of the world, melting. Greenland is the largest island on Earth. It sits between the Arctic Ocean and the North Atlantic, directly upstream of the AMOC's critical sinking zones, and it holds roughly 10% of all the fresh water on the planet, locked in an ice sheet that in some places is more than 2 miles thick. It is also melting faster than at any point in the modern record. Greenland's ice sheet loses mass through two main processes: surface melting, where summer warmth melts the top layers and the water runs off into the ocean, and calving, where glaciers that extend to the coast break apart and dump icebergs directly into the sea. Both processes have been accelerating. In recent decades, Greenland has been losing ice at a rate several times higher than what was observed in the 1980s and 1990s. The acceleration is tied to both increased summer air temperatures melting the surface and warmer ocean water eating at the undersides of coastal glaciers from below. Each ton of ice that Greenland loses becomes fresh water in the North Atlantic. The math here is not subtle. Greenland is shedding hundreds of billions of tons of ice beyond snowfall replenishment every single year. That fresh water is flowing into the exact region where the AMOC depends on salty, dense surface water sinking to the seafloor. The fresh water dilutes the salinity. The sinking weakens. But the Greenland-AMOC relationship is not just a one-way input, it is a feedback loop. A weaker AMOC means less warm water pulled north in the Atlantic. That sounds like it should cool Greenland and slow the melt, but it also means changes in atmospheric circulation patterns over Greenland that can actually warm the island's surface in certain seasons. And a warmer southern ocean from the hemispheric heat redistribution caused by AMOC weakening puts more warmth in contact with Antarctic ice, not Greenland, but adding to total global sea level and overall warming pressure. The connections are complex and the net effect is still studied intensively, but the core dynamic is physically clear. More Greenland melt means more fresh water in the North Atlantic, which weakens the AMOC, which changes conditions in ways that do not reliably slow the melt. There is no self-correcting mechanism that automatically resets this process. The planet does not have a thermostat that kicks in when the AMOC starts slowing and sends Greenland back into a stable freeze. What it does have is a past, and that past contains examples of exactly what happens when the AMOC loses its footing. Examples preserved in ice and rock with a precision that still surprises the scientists who read them. The AMOC has not always run at its current strength. Earth's climate history is full of episodes when the overturning circulation weakened dramatically, or essentially stopped. Those events are recorded in some of the most detailed natural archives scientists have access to. Ice cores drilled from the Greenland ice sheet contain compressed layers of ancient snow going back hundreds of thousands of years. Each layer traps air bubbles, dust, chemicals, and isotopes that reveal the temperature and atmospheric conditions of the time when that snow fell. Reading an ice core is like reading a climate diary written by the planet itself. Ocean sediments preserve a different kind of record. Tiny shells of ancient single-celled organisms called foraminifera sink to the seafloor when they die. Their chemical composition records the temperature and salinity of the water they lived in. Layers of sediment drilled from the ocean floor contain centuries or millennia of these shells, stacked in order, readable like pages in a book. Cave deposits, called speleothems, record rainfall patterns going back even further. Their chemical layers show how monsoons shifted, how droughts arrived, how rainfall belts moved. All of these archives tell the same story about what happens when the AMOC weakens dramatically. During the last glacial period, between roughly 100,000 and 12,000 years ago, the North Atlantic experienced a series of abrupt climate events called Dansgaard-Oeschger events. In these episodes, Greenland temperatures jumped by as much as 27 degrees Fahrenheit within decades, not centuries, decades. Those rapid warmings are understood to reflect changes in AMOC strength. When the circulation strengthened, it flooded the North Atlantic with warmth. When it weakened, the warmth pulled back and temperatures plunged. The ice cores show these transitions as sudden sharp jumps in the layers. A slow stable signal, then a jump to a completely different level, then sometimes another jump back. The transitions look violent in the data. They were violent in reality. Monsoon records from caves in China, Venezuela, and the Middle East all show correlated disruptions during the same events. When the AMOC shifted, rainfall patterns thousands of miles away responded. These past events are not perfect analogies for today. The planet's ice sheet configuration was different. The background climate was different. The forcings driving the changes were different. But they confirm one fundamental thing. The AMOC is capable of abrupt transitions. The Earth has experienced them. The consequences were global. And one of the most dramatic examples in the entire geological record happened right at the end of the last ice age, when the world was just beginning to warm into the conditions humans have lived in ever since. 12,000 years ago, the last ice age was ending. Glaciers were retreating, temperatures were rising. The climate was moving toward the warm, stable conditions that would allow human civilization to develop. People were beginning to shift from purely nomadic life toward early farming. The world was thawing. Then something interrupted it. In a matter of years to decades, temperatures in parts of the northern hemisphere dropped sharply. The warming stopped. The North Atlantic went cold. Glaciers stopped retreating and in some regions started advancing again. The climate reverted toward Ice Age conditions for roughly 1,300 years. Scientists call this event the Younger Dryas. The cause is well understood. As the Ice Age ended, enormous glacial lakes formed at the edges of the retreating North American ice sheet. These lakes held vast quantities of meltwater. At some point, a drainage pathway opened, and one of these lakes released a massive pulse of fresh water into the North Atlantic. The fresh water flooded the sinking zones. The AMOC weakened dramatically or essentially shut down. The heat that had been flowing north through the Atlantic was cut off. Europe and the North Atlantic region plunged back into cold conditions. The tropical rain belts shifted south. Monsoons failed across wide regions. For the people living through it, the Younger Dryas would have been catastrophic. The warming world they had been experiencing reversed. Growing regions that had opened up became hostile again. Species that had been expanding their ranges retreated. Then, after about 1,300 years, the AMOC recovered. It switched back on. Temperatures in Greenland rose by about 18 degrees Fahrenheit within a decade. The Younger Dryas ended. The whole episode is a perfect natural experiment in what AMOC collapse does to the planet's climate, and it matches almost exactly what physical models predict. A freshwater pulse weakens the sinking. The overturning stops, the heat shuts off, the world gets cold and dry in the wrong places. Then, when the freshwater pulse ends and salinity can recover, the system restarts. Scientists are not suggesting today's situation is identical to the Younger Dryas. The freshwater input then was a single massive pulse from a draining glacial lake. Today's freshwater input is slower, more sustained, coming from gradual Greenland melt and increased Arctic precipitation. But the mechanism is identical, and the outcome of the natural experiment is preserved in the geological record with enough clarity that anyone can read it. The question haunting modern AMIC research is whether the slower, sustained freshwater input of today could push the system toward the same place the Younger Dryas pulse did. The answer depends heavily on one key difference between the ancient past and right now. The Younger Dryas came from the outside. A glacial lake drained. A pulse of fresh water hit the North Atlantic. The AMOC responded, then the pulse stopped. The fresh water dispersed. The ocean's natural salinity recovered. The AMOC restarted. The forcing was external, temporary, and eventually self-limiting. Today's forcing is different in a fundamental way. It is not coming from a single draining lake. It is coming from a planetary warming that is ongoing, self-reinforcing in its own right, and driven by a cause that will not simply stop the way a glacial flood eventually stops. Greenhouse gas emissions are warming the entire planet. That warming melts Greenland continuously, year after year, with each decade of warming pulling more ice mass off the ice sheet than the decade before. Unlike a lake that empties once and is gone, the Greenland ice sheet is a reservoir that keeps releasing fresh water as long as temperatures stay elevated. There is no point at which the forcing naturally reverses unless humans actively reduce greenhouse gas concentrations. The lake that fed the Younger Dryas eventually ran dry. The atmospheric greenhouse effect, absent deliberate human action, does not run dry. This means the fresh water pressure on the AMOC is not a temporary insult to a system that will recover once conditions normalise. It is a sustained push in the same direction, year after year compounding. Additionally, warming itself directly weakens the AMOC in a second way. Warmer surface temperatures in the North Atlantic mean the water arriving at the sinking zones has lost less heat by the time it gets there. Less cooled means less dense. Less dense means weaker sinking. Even without any freshwater input at all, warming alone would reduce the AMOC's overturning strength over time. Today's AMOC is being pushed from two directions simultaneously. Freshwater from Greenland diluting the sinking zones, and warming temperatures reducing the density contrast that drives the overturning. Both effects are driven by the same underlying cause. Both effects grow stronger over time as long as greenhouse warming continues. The Younger Dryas showed what a freshwater pulse can do to the AMOC. Today's situation involves a slower but sustained and growing version of that same push, combined with thermal weakening that the Younger Dryas forcing never included. This is the scientific reason behind the title of the research driving this video. Something far worse than a normal Atlantic shift is already underway. A normal Atlantic shift is variability. What scientists are now watching is structural, and governments, for the most part, are still responding to the old version of the story. The science has moved faster than the policy. Governments and international institutions that set climate adaptation plans largely built those plans around the moderate model scenarios from IPCC reports and older consensus summaries. Those scenarios treated AMOC weakening as a gradual late-century issue, unlikely to produce abrupt changes before 2100. The newer research has not fully reached the planning tables yet. Infrastructure investment cycles in wealthy countries typically run 15 to 30 years. A decision made today about coastal flood protection, agricultural subsidy structures, city zoning, or energy grid capacity will shape outcomes through the middle of this century. If that decision is made using sea level projections that underestimate AMOC-driven regional rise by a foot or more, the investment will be undersized from the day it opens. The mismatch is compounding. Every year of planning based on too optimistic projections is a year of underinvestment in resilience against outcomes the newer science says are more likely than previously thought. This is not unique to the AMOC problem. Climate policy has consistently faced a lag between scientific understanding and institutional response. But the AMOC adds a specific challenge that most climate risks do not carry. The possibility of an abrupt, non-linear change means the planning timeline could compress suddenly. A gradual threat can be managed incrementally. A tipping transition changes the problem faster than incremental responses can track. Some European governments have begun explicitly factoring AMOC risk into long-range assessments. The Netherlands, which sits below sea level and has been engineering against water for centuries, has been among the more proactive. Scandinavian nations are aware of the direct temperature exposure. But these are exceptions, and their planning still largely relies on the moderate scenarios. Developing nations in the tropics and Sahel, which face the rainfall and food security consequences of AMOC disruption, generally have far less capacity to prepare and adapt. They are also the nations least responsible for the greenhouse gas emissions driving the problem. The asymmetry between those who cause the AMOC stress and those who will bear its harshest consequences is one of the most uncomfortable dimensions of the entire issue. International climate negotiations have not specifically grappled with AMOC risk at the policy level in a way that matches what the science is now saying. The framing in most public discussions remains one of gradual, manageable change. The research now suggests a tipping element of global importance may be closer to its threshold than the official documents reflect. The gap between where the science stands and where the policy stands is not a gap between optimists and pessimists. It is a gap between an institutional response built for one version of the future and an updated science pointing toward a more dangerous one. And there is one lever that could still close that gap if applied quickly enough. The AMOC is not going to be fixed with an engineering project. There is no pump large enough, no barrier possible, no direct intervention that could substitute for the natural density-driven overturning that has run for millennia. The only lever that can meaningfully reduce the risk is the one that addresses the root cause, reducing the rate at which the planet warms, which reduces the rate at which Greenland melts, which reduces the freshwater input to the North Atlantic sinking zones. That means cutting greenhouse gas emissions deeply and quickly. The connection between emissions reductions and AMOC stability is not direct or immediate. Even if humanity stopped emitting carbon dioxide tomorrow, there is already enough warming locked in the system to continue melting Greenland ice for decades. The ocean absorbs heat slowly, and that absorbed heat continues influencing ice melt and thermal weakening of the AMOC long after surface emissions change. But the trajectory matters. A world that continues high emissions through the second half of this century drives Greenland melt at an accelerating rate and pushes the AMOC through its most vulnerable zone under maximum stress. A world that cuts emissions sharply reduces the total freshwater input, slows the thermal weakening, and gives the system more time operating further from its tipping threshold. The difference between those two trajectories in terms of AMOC stability is substantial. Models that distinguish between high and low emissions scenarios for AMOC outcomes consistently find that lower emissions reduce the probability and severity of major weakening or tipping. This is not a guarantee in either direction. The AMOC may weaken significantly even under aggressive emissions reductions, because of the warming already in the pipeline. Conversely, even under high emissions, collapse may not arrive before 2100 in all scenarios, but the probability of a tipping transition drops meaningfully in lower emissions futures. For scientists who study the AMOC, this is the clearest and most direct message. Reducing emissions is not just about global temperature targets, it is specifically and directly about preserving the stability of one of the most important climate systems on Earth. Alongside emissions, preserving and potentially restoring Arctic sea ice and reducing other regional warming feedbacks would help. Some researchers have explored whether deliberate freshwater diversion or other geoengineering approaches could reduce the freshwater input to the North Atlantic sinking zones. These ideas exist at the theoretical level and face enormous practical, political and ecological complications. The realistic near-term answer remains the same one. Emissions drive warming. Warming drives Greenland melt. Greenland melt drives freshwater input. Freshwater input weakens the AMOC. Addressing the first thing in that chain is the only way to reduce pressure on the last. And if the chain runs to its end, the world that emerges on the other side is not an apocalyptic fiction. It is a reorganized reality that billions of people would have to live inside every single day. No flash. No single dramatic moment. An AMOC collapse does not arrive the way a disaster movie imagines it. What it looks like is something harder to film and harder to escape. Farmers in France plant the same wheat varieties they have been growing for 30 years. The yields start falling, then they fall again. The frosts come later in spring and earlier in fall. The window between them shrinks until the variety no longer works in that region. A generation of farming knowledge becomes outdated within one farming lifetime. The French government, along with every other northwestern European government, spends heavily on heating subsidies during winters that are measurably colder than the 20-year average. Energy prices rise. Energy systems built for mild winters strain under demand they were not designed to meet. Blackouts happen in northern cities during cold snaps that would have been unremarkable a generation earlier. Insurance companies working along the American East Coast review their flood models. Again. South Florida coverage becomes too expensive for most homeowners. Then unavailable. Then the federal backstop program expands. Then it strains. Property values in the lowest lying areas begin the long process of decline that economists have already been modelling. In the Sahel, the monsoon window narrows by 2 weeks. Then 3. A region where the entire agricultural calendar is built around a monsoon that lasts 3 months cannot easily absorb a 20% reduction in its length. Harvests fall, aid programs scale up. Political pressure in already fragile states increases. None of this is a single catastrophic moment. It is the texture of a civilization slowly discovering that the conditions it organized itself around no longer apply. Not everywhere, not simultaneously, but persistently, in more places, in more years, until what used to be a bad year becomes the average year and the average year becomes a crisis. Supply chains absorb localized shocks. They do not absorb simultaneous shocks in multiple major producing regions. Markets pass costs down. The people at the bottom of the cost chain have the least ability to absorb them. This is the scenario that serious AMOC researchers are most concerned about. Not a day of catastrophe, but a decade of accumulating dislocation. Problems that compound each other. Agricultural stress feeding food price shocks, feeding political instability, feeding reduced capacity to manage the very climate challenges driving the stress. The system does not collapse in a moment, it degrades, which makes the question of what we are still waiting to learn all the more urgent. The most haunting question in AMOC science is not whether the system is weakening. That is confirmed by direct observation across 2 decades and multiple independent data sets. The most haunting question is whether the point of no return has already been passed. Scientists define the point of no return for the AMOC as the moment when the salt advection feedback, the self-reinforcing loop where weakening drives further weakening, becomes strong enough to sustain itself without additional external pressure. Before that point, reducing the freshwater input by cutting emissions could allow the system to stabilize or slowly recover. After that point, the transition continues even if the external forcing stops. No scientist today can say with certainty whether that threshold has been crossed. The observational record is too short. The models disagree on where exactly the threshold sits. The early warning signal analyses are contested. The IPCC's last full assessment said abrupt collapse before 2100 was unlikely. Newer research from 2024 and 2026 has made that reassurance harder to hold with confidence. What is known is this: the AMOC is measurably weaker than at any point in over 1,000 years of reconstructed records. The freshwater input from Greenland continues to grow. The best performing climate models now project a weakening of 43 to 59% by 2100. The system is showing mathematical signatures in some analyses that resemble a system losing its ability to recover from disturbances. None of that is a definitive statement that the point of no return has been reached, but it is also not a reason for confidence that it has not. The most honest summary of where science stands today is this: the AMOC is in trouble, the direction of change is clear, the severity depends on choices about emissions that are still being made. The timing of potential tipping is uncertain in a way that cuts toward danger, not toward comfort. And the consequences of underreacting if the risk is real are dramatically larger than the consequences of overreacting if the risk turns out to be lower than feared. Climate systems do not send press releases when they cross their thresholds. They do not announce the point of no return. They just keep changing. The data keeps arriving. And the scientists watching it keep asking whether the signal they are seeing is the warning or the outcome. The Atlantic is not sending reassuring signals, and the ocean beneath our feet has been running this engine since before humans walked the Earth. It has never had to run it while we were watching. Until now.